We'll start our video here with a quick recap of the first derivative test. So the first derivative test, you find your first derivative, you find where your first derivative is equal to 0, and if it is increasing to decreasing, in other words, if your derivative changes from positive to negative, you'll have a maximum. If your derivative changes from negative to positive at that point, you'll have a minimum. And this is called the first derivative test. So we wrote it in other words, if it changes from increasing to decreasing, that point's obviously a maximum. If it changes from decreasing to increasing, that point is a minimum. So we have a parabola. The parabola is opening down. So based on previous knowledge that we have, you would already know that the vertex is a maximum. This question is asking us to find that maximum point and to prove that it's a maximum using the first derivative test. So first of all, if something is going to be a stationary point, we find the derivative, and we set our derivative equal to 0, solve for x, and we get that x is equal to 5 over 2. So we know that 5 over 2 comma something, thank you, is going to be, in this case, our vertex. How do we find the y-coordinate? Well, since that's a point on the actual parabola, how do you find points on the parabola? You're going to have to plug in 5 over 2 for x. So can you see that you would have, just mental math here, plugging in 5 over 2, you get negative 25 over 4 plus 25 over 2 minus 7. Whew. So what is that going to be? 25 over 4 plus minus 7. 25 over 4 is 6 1/4 minus 7, negative 3/4. Maybe? Looks good. If it's wrong, we'll never know, because no one's going to check it. It's not like you guys go home and check this. It's like, but you could check with the calculator. Okay? So if someone wants to check it, that would be great. But we'll go with that for now. So at this point at 5 over 2, because that's where we had our derivative equal to 0, to show that it's a maximum, we need to show that a derivative changes from positive to negative. So we choose a point prior to 5 over 2. For example, 0. Plug in 0, and into our derivative, we get 5. We know this section is positive, so that tells us our graph is increasing. If you plug in something larger than 5 over 2, like 3, plug 3 into your equation, you get negative 1. This section is negative, meaning that it's decreasing. Now, with the first derivative test, you need to write a statement. The statement will look like this. Since f prime at 5 over 2 equals 0, and f prime of x is greater than 0 before x equals 5 over 2, and f prime of x is less than 0 after x equals 5 over 2, we know that this point is a maximum. So that statement shows that you know every part of the first derivative test. Because there's always two things you have to say in the first derivative test. You have to say that the derivative is equal to 0 at that point. That's what makes it a stationary point. And secondly, you have to show that it's changing from positive to negative. So here's one for you to try. Another parabola. We know this parabola is opening up, so you should know that the stationary point or the vertex will be a minimum. But can you show it using calculus? And can you find it using calculus? And then you just need to write your statement. Do you need me to show the statement on the last one? Yeah. Well, the one that you just wrote was for this one.
Oh, no. Okay.
There you go. And so the question is right there.
So I finished it.
Well, Moby, you did this is the answer for the other one. And I put the solution up on the board. So once you're done, you can check to see how you did. Good to go. So on your calculator, if you have a graphing calculator or if you use Desmos program, there are ways to find maxes and mins. You've probably done this in other courses. But let's just say I have some parabola. So if I go to my graphing calculator here, just to show you, who does not have a graphing calculator? Okay, so then you would look on Desmos using the Desmos app to do this. But I'll show most of us here do have a graphing calculator. So if you wanted to find a maximum or minimum on your calculator, I know exactly what I'm going to do. I'm going to type in the equation that we did where we did mental math. This might be really disappointing for me because I might find out that my vertex was wrong. I shouldn't do it? Or it was right? It was right? Okay. Well, we can do it then and then feel extra good. So if I type in, I go to my calculator, I hit y equals, I clear out these other equations, clear, and I type in negative x squared plus 5x minus 7. Wow, that is not an x. There we go. And you hit graph. There's our parabola. If I want to find this maximum, I can hit the second trace button because above it says calculate. In this case, I want to find a maximum, number 4. Using your cursor, your maximum is going to be about there. You need to start, it says, on the left side of it. You can be anywhere on the left and push enter. Some of the newer calculators will put a dotted line. Older calculators will just draw an arrow at the top. Then you need to go to the right of it. And for those of you that like computer science, okay, what's going to happen next is the calculator is going to go through a series of algorithms checking whether it gets bigger or smaller between those 2 points. Okay? And what it's going to do as it checks if it gets bigger or smaller is going to disregard one of the previous points and slowly make the interval smaller and smaller and smaller until it is happy enough, I think that's a computer science term, happy enough that it's close enough. And then it will say, this is what I think your answer is. So when we push enter after the guess, it says the maximum happens at negative 0.75, which is exactly what we found, and at 2.5000000009, which is an error because we, oh, okay. So each of our calculators established happiness at different levels. Happy enough, okay? 2.5 is the right answer. We figured that out with calculus. It's kind of a little bit, I'm smarter than my calculator moment. It used an algorithm and it got close, but we used calculus and got closer. Okay? We did one calculation to get our answer, and most likely the calculator performed thousands of calculations. Ooh. It got the wrong answer faster than we got the right answer. Oh, we'll give it that. We'll get okay? But it's just showing you how you can get your answer with your calculator. So we have looked at stationary points that are maximums and minimums. Sometimes you get a stationary point of inflection. And I showed you what this was already with the most common graph, the x cubed graph, where the tangent line is flat, but it isn't a maximum and it isn't a minimum. How do we know and how do we define this as a stationary point of inflection? Well, your derivative is still 0. Right? We look at x cubed. We find the derivative. We set our derivative equal to 0 and solve. X is equal to 0, so we know that at this point, 0, 0, the derivative is equal to 0. That means the tangent line is flat. It has a slope of 0. But if we did our number line with 0 on x cubed, the derivative is 3x squared. Can you see that if you plug in a negative number or a positive number, when it gets squared, it's going to be positive. This section is positive. This section is positive. Your x cubed graph, which you know is always increasing. And so if the gradient of the curve on either side has the same sign, in other words, it's always increasing or always decreasing, this is what's called a stationary point of inflection. The graph still changes from concave down to concave up, and that's what an inflection, we're going to learn that that's what an inflection point does, where it changes its curvature from concave down to concave up or vice versa. But it doesn't stop increasing. And what's going to always happen is if there is a stationary point of inflection at a certain point, here I chose x1, the second derivative will also always be equal to 0 at that point. So now we have all of this information, which isn't that much. We can find our derivative, find our critical points, find out where something is increasing or decreasing to find out if those critical points or stationary points are maximums, minimums, or inflection points, stationary points of inflection, and we'll be able to graph it quite accurately. Okay? So you're asked to graph cubic ones in grade 12. But you can only graph cubic ones in grade 12 if you're able to factor them. And you're only able to graph them if you kind of are a little wishy-washy and say, I don't care where maximums and minimums are. That's grade 12 graphing. The only thing in grade 12 that you would know from this one is that it starts down here and ends up here, and it might do something like that in the middle, but I don't know exactly where or when. I would try to find my x-intercepts, but that only works if it factors nicely. And this one does not look like it factors nicely. So the best I could do is use my graphing calculator. Well, welcome to calculus. Calculus says, if you find the derivative and you set your derivative equal to 0, this one I can factor out a common factor of 3x. I get two places where the derivative is equal to 0. Those will be stationary points. We don't know yet if they're stationary points of inflections, if they're maximums or minimums. But we do know where those points are. We've got 0 comma something and negative 2 comma something. If I want to know exactly where they're on the graph, I'd plug them back into my original equation. 0 comma 1. Negative 2 comma, well, negative 8 plus 12 is 4 plus 1. Negative 2 comma 5. We're going to find out what kind of points are those. So I'm going to put them on a number line. I'm going to put negative 2 and 0 on a number line. I'm going to check if my graph is increasing or decreasing. So I plug in something less than negative 2 into my derivative. Personally, I like using the factored part because then you don't even have to do much mental math. Like plug in negative 3. Would you agree that this section would be negative? And this section would be negative. And a negative number times a negative number will always be a positive number. So this section is increasing because my derivative is positive. If I plug something between negative 2 and 0, like negative 1, this will still be negative, but this section now is positive. A negative times a positive is always negative. This part is decreasing. So I now know from the first derivative test that negative 2 comma 5 is a maximum. Yeah, I was about to say maximum. I was about to write maximum. Oh, I didn't, but I wrote minimum. Okay. Negative 2 comma 5 has to be a maximum. And then, if I plug in something larger than 0, like 1, this section will be positive, this section will be positive, this whole part will be positive, meaning it's increasing again, making this 0 comma 1 a minimum. As far as graphing this, we know that at 0 comma 1 we have a point. That's a minimum. We know that at negative 2 comma 5 we have a maximum. What does our graph look like? And this is more accurate than your graphing from grade 12 pre-calculus. Yeah, you should just do that on all your tests and see what Mr. Yeah. Yeah, it'll go over well. Usually we also label all of our intercepts. The y-intercept is already done. The x-intercept, unfortunately for this one, is not easy to find. The best that you could do would be to use either your graphing calculator or you could use the cubic formula, But yeah. Just like there's a quadratic formula, there's a cubic formula. And they get really nasty really quick. Yes. I have. It's not. Once you look at it, you just look away. Okay. X4 minus 4x cubed. Yeah, this notation is the same thing as f of x equals, but it's just a different notation. One of the things I try to do in your notes is find different notations from different textbooks in different places, just so you just get used to seeing different things. Okay? I would just change it to this. Okay? Technically, the derivative notation for this would be f prime sends x to what? Okay, but it's okay to see different notations, and it's okay to say, I don't like that notation as much. I'll change it back to something I like more. So our derivative would be 4x cubed minus 12x squared. Just a recap. You actually know a fair bit of this from, I'll do it at the end. I'll recap what you know from grade 12 at the end. First, we'll do it with calculus, because overall, we're going to come to the opinion that graphing with calculus is better than graphing how we used to. And generally speaking, from most mathematicians' points of view, graphing is a lesser endeavor than solving something. I don't know what it is. Drawing, sketching. There's our derivative. We set our derivative equal to 0. Do you see that you could factor out a 4x squared in common, leaving you with x minus 3? So you get x equals 0 and x equals 3 as our two solutions. So we know if I plug in 0, which happens to be 0, 0, and if I plug in 3, 81 minus 108, negative 27, good. We're going to find out if those are maxes, mins, or stationary points of inflection. The values that we're going to put on our number line are 0 and 3. And since that is a number line, the order is important. You have to put 0 before 3. Everybody's okay with that? Yeah, sure. I'll just use reverse grades. We can do that. And I'm fine with that if you're fine with that. I don't know how Power School will react. It might have some issues, but we won't worry about that too much. We should try it. Let's try it with your grades. If it doesn't work, what I'll just do, so if you get, like if I was going to give you negative 19 out of 20 on one assignment, but on a previous assignment I gave you 20 out of 20, I'll just combine them and give you 1 out of 40. To find the actual points we plug into the original equation. Yeah, so again, when you're actually, these are points on the graph, right? And anytime you're finding points on the graph, you're always plugging that x value back into the original equation. When you're trying to find out where your graph is increasing and decreasing. So I'm going to plug in negative 1, but I will plug that into, this will be positive, negative 1 into here, negative. This section is negative. I'm plugging that into my derivative. I plug in positive 1. This is still positive. This is still negative. Interesting. Still decreasing. What does that tell us at the point 0, 0? Stationary point of inflection. Wow, that seems too long. We should call it a SPOI. Well, it's stationary though, so it's more than just an inflection point. Do you like SPOI as an acronym? Yeah? So there's our SPOI for today. And then at 3, if you plug in something bigger than 3, this section's also positive, meaning that your graph is increasing. So what do we have? Okay. If we go to graph this, we have 0, 0. And we've got 3, negative 27. Our graph is decreasing, so it means it's coming down. Flattens out, comes down again, swings back up, and this is our final graph. In this question, you can actually find this point without a calculator. That's your x-intercept. How do you find, in fact, now we're going to go back to grade 12. How would you have graphed this in grade 12? In grade 12, you would have recognized it as an x to the 4 graph, so you would know that its end behavior looked like that. You would have then tried to find your x-intercepts. You would have found your x-intercepts by putting in 0 for y and solving. And this one, you could factor out an x cubed, leaving you with x minus 4. I'll relabel 0, 0. And your two x-intercepts, your x-intercept of 0 has a multiplicity of 3. So when an x-intercept happens more than once, right? You could have x equals 0 happen 3 times. If you wrote it in an expanded form as 4 factors, it would be x times x times x times x minus 4. And so we say that when an x-intercept happens more than once, it has a multiplicity of whatever the exponent is of that x-intercept. For those of you that have taken grade 12, anytime your multiplicity is 1, as is x equals 4, your graph goes straight through at that point. Anytime your multiplicity is odd but bigger than 1, in grade 12 we just described it as a bend in the graph. It bends at that point. We now know in grade 12, in calculus, that it's officially a stationary point of inflection. When it has a multiplicity that's odd, bigger than 1, it will always bend. The severity of the bend increases as the odd number increases. If the multiplicity is even, it would bounce off your x-axis. Like, think of an x minus 3 squared graph. X minus 3 in brackets, right? The vertex bounces off your x-axis. So this graph, using grade 12 pre-calculus, you would have had these two x-intercepts. You would have known it bent here. You just wouldn't know how far it went down to 3, 27. Now that we have calculus, we get exactly where that minimum is. We know why the bend is there. Is this class unfortunate? Aiden. You're stuck on the graphing thing. You know what? I've been there. I can say, as someone who's studied a fair bit of mathematics, that I also like, ooh, a graphing unit. Go into the back room, swear a little bit, come back. Yeah, graphing is not as much fun. But over the years, being able to see something as a graph versus an equation, it's just another lens that helps you understand something, and it's very powerful. So, yeah.